Hello and welcome to another ANSYS Workbench tutorial. In this particular tutorial we're going to look at the stresses that develop in a bolted joint. We will look at the stresses that develop in these four bolts as well as the normal or bearing stresses that develop in the members. This example problem is given by example 8.7 in your Shigley textbook. I hope you enjoy the video. So once you've opened SpaceClaim, you can close the pop-up window. Then I like to right click, select new sketch plane, click a point in the XY plane and click on the grid, then click plan view. I now want to change this minor grid spacing. Right now the default is 1 millimeter. I want a grid spacing of 10 millimeters between each small grid. So I'll go to File, SpaceClaim Options. This takes a second to come up. I'll click on Units. I'm going to leave my units in millimeters, but I'm going to scroll to the bottom, and instead of having a minor grid spacing of 1 millimeter, I'm going to enter 10. Now I'm ready to start to build my cantilever beam. I'm in sketch mode, so I'll come to Rectangle. I'll start in this corner. My rectangle is 200 millimeters in that direction, and then tab and 550 millimeters in that direction. Now I'm ready to escape out of that and create some circles. I'll use these XY coordinates that are listed down here to help find the center of this top circle, and it's going to be at a 50 and a 40 based on the geometry. So now that I have that center, I can click and drag. And this is a 16 millimeter diameter circle. Now I can escape out of the circle command and come to move. I can click on the circle and control drag, and I'll drag that down 120 millimeters. Now I can control click on the top circle and then control slide both of those circles together, and that will be 150 millimeters. So now I can escape out of that, rotate my geometry, click on pull, and pull this geometry 15 millimeters. Now I have my beam build. I'm ready to build the vertical support. So I'll escape out of pull mode. I'll rotate this around, and I should have escaped one more time. Then I'll control middle mouse button and drag. I'll click on sketch mode and select that sketch plane, and I'll look at it directly in the Z-axis. I'll come to rectangle, and I will start this rectangle in the vertical axis and drag it, and this will be a 250 millimeter tab, and maybe I'll make that 260, 270 to get a little more on the bottom, so I'll go 270, enter. And then on the top, that's going to be 250, 250, enter. Now I'm ready to go ahead and escape out of this and rotate it and pull this member out. So I'll click on pull, I'll select that plate, then I'll have to control select the top and the bottom, and then I can drag this out 10 millimeters. Now if you look over here, I have surface and one solid, but I want these two to be separate solids. So I need to come and split this. So to split this, I'll escape out and I'll create a plane where I want the split to occur. So I'll come up to plane and I'll select this face. Now I can click on move and move this plane, and I'll move the plane in that same 10 millimeters. Now I can escape out of this, and I can come up to split body, and I'll click on the body, and then I'll click the plane. And you can see now that I have created a new solid. So I have two different solids over here. This top one, and then my bottom solid. I'll be able to delete this surface in this plane, or I can just click to deactivate them and not see them. Now I'm ready to go ahead and generate the cylinders. So I'll click on sketch mode. I'll look at this in the Z-axis, and I'll come and click on circle, and I'll click the sketch. Now I'm ready to click on my circle, and I'll create a 16 millimeter diameter pin. I will rotate this a little bit, and I will pull that pin out 25 millimeters, as that is the thickness of the vertical support and the cantilever beam. So this will be 25. Enter. Now I can copy that, so I'll box select, and I can either do it that way, or once I have it I can come and click move and then control slide, and control slide. Now I have 4 pins built, and I can come up to align, and I'll scroll in a little bit, and I can find the center axis. So I'll pick on select, find the center axis of this cylinder, and click on align. Now that I have the center axis, I can align that center axis with the center axis of the holes there, and then I can align this top face of the shaft with the face of the plate. And I'll do that same thing for all of these pins. So now I can look at this in the Z-axis, and I have my cantilever beam, I have pins. I don't need to worry about putting nuts or heads on these bolts because I'm not going to apply any pre-stress or preload to the bolts. I simply want to look at the shear stresses that develop in the bolt, and then the bearing stresses that develop on the cantilever beam. So I can come over here and I can actually delete this plane, and I can delete this surface and have a little bit cleaner geometry. So that's concluded my work in space plane. I'm ready to open mechanical. So after opening ANSYS Mechanical, I can check my geometry and see that all of my systems have been brought in correctly. I can go ahead and rename these if I'd like. I can name this one rename as beam. This next one I can click and then right click, rename vertical support. I'll just call it vert. And then this first one I can call bolt number 1. So right click, rename bolt 1. Then I can click, right click, rename, I'll call this bolt 2. Click, right click, rename bolt 3. And finally right click, rename bolt 4. Enter. So my geometry's been defined now, and I have better names here. I could have also done that in space plane. I'll close this. My coordinate systems are okay. I need to look at my connections and make sure my contacts are in good shape. So my first contact region is between the beam and the vertical member. It will be listed as bonded, and I won't want that, but I'll change all of them, or many of them, at the same time. So I certainly need this contact, so that works. Then I have a contact between the pin and the cantilever beam. And I have a contact between the pin and the beam in hole 2, then hole 3, and then hole 4. So all those look great. And then I'll come down to the vertical member, and I have a pin contact with bolt 1, 2, 3, and 4. I want all of these to be friction, so I'm going to click on the top, then shift click the bottom, and then I can right click, and or actually I can just click on again the top, shift click the bottom, and now I can come to bonded, click the drop down and click frictional, and then my friction coefficient I can enter as a 0.2, and that changed all of the contacts together, so I'll leave them as that. I will change the one vertical member, and on this I will have the behavior as, instead of program controlled, I will have it as a symmetric pair. Now the two plates will essentially talk to each other in both directions. So I'm ready to go ahead and click on mesh. So I'll click on the z-axis to look at this in the z direction. Now I can right click mesh and left click generate mesh to see what the default mesh looks like. I can see that it has quite a bit of element density in the bolts, not too much element density in the members, especially around the bolt. So I'm going to go ahead and right click on mesh, insert refinement. Now I'm going to come and rotate this a little bit and click on body select, click on the first bolt, control click, select all the other bolts, and then right click and hide body. Now I'm going to select these inner surfaces here to refine the mesh on those inner surfaces. So I'll come back up to surface select, and there's a surface here on the vertical support and a surface on the beam. So I'll click the first surface, control click, and that's the wrong one. So click, control click, click, make sure it's highlighted, control click, click, and all these clicks have been holding down the control, so I should have, when I apply that, 8 faces, and I do. So my mesh refinement's done. I'm also going to click on mesh and scroll down, and where it says sizing, I can open the sizing, and I can change the relevance center from medium to fine, but I'll look and see what medium does for now and see if that will be a good enough mesh. So I click on update. My mesh is completed. I can look again at this straight on, and it looks like I have plenty of element resolution around my holes now. So I'll go ahead and right click and click on show all bodies, and now I'm ready to go apply my boundary conditions and my loads. For boundary conditions, I'll go ahead and I'll fix the bottom and the top of the vertical support. So I'll come to static structural, right click, insert fixed support, and I'll click this vertical face, rotate around, and click the bottom vertical face, and I need to make sure I hold the control button down so I get both faces selected. So control select, and then I can come over and apply, and it gets the two faces. I need to now apply my load at the end, so I will right click on static structural, insert force. I'll click on, rotate this around and click the face, click apply, and I'll change this to components. So click on vector, click the drop down components, and now I'll scroll down and change the Y component to apply a load of 15 kilonewton, 16 kilonewtons. So on Y, I'll type in -16000 for newtons, and I will hit enter. and you can see that I have the right units here. I have my force applied. If I click on static structural, I can see my boundary conditions. Now I'm ready to go ahead and hit solve and come up with my outputs. So if I click on solution, the stresses I want to see are the von Mises stress, then I want to see a normal stress, I want to see a maximum shear stress. I can look at deflections just to kind of get a feel for if this solution makes sense, and all of these others I'm probably okay without doing. So now that I've selected these, I'm ready to right click on static structural and click solve. So our solution has been obtained. We have green check marks by all of our outputs. We can look at them in general and see if they basically make sense to us. This deformation does. We can see that the maximum deformation is out here at the end of the cantilever beam. To compare some answers with the solution in the textbook, I want to look at the maximum shear stress. I want to look at that maximum shear stress on the bolts. So what I'll actually do is click on solution, and I'll click on body select. I'll click the cantilever beam, and I'll control click the back vertical support, then right click and hide body. Now I have just my pins, and I can look at the maximum shear stress in those pins, and I can just pick one pin, for example, and look at it. I can come and look at it straight on and then make a cut and come up to section and section this beam or this pin, and now I can rotate that around and look at the back. Now I can see all of that pin, and I can come up to probe and then click the drop down and click on all bodies, and I can start to probe those results, and you can see that it's difficult to see, but there are several values. I'll control roll this to the middle, and in this darker green I'm about 1.2 e to the 8. In the lighter green 1.1 e to the 8, and comparing that with the answers in the book of 104 MPAs, those results are very close. So it looks like the shear stress in the bolts has been computed correctly. So I can go ahead and right click and click show all bodies, look at my z-axis. Now I need to come down here to my section plane and uncheck that so that I look at the full body again, and I don't want to keep looking at a section plane. Now I want to look at the bearing stress, and I'll look at the bearing stress on the vertical member. So I'll come back up to static structural. I'll click on body select, and I'll click on each bolt or pin, and then I'll click on this front beam, and I'll right click and hide body. Now I can rotate this and zoom in on one hole and look at the normal stresses. I can come back up and select probe, and if I look at these values here and I go to the hot spot, I probably want to rotate this and look over here where the blue is for the bearing, or be getting pushed on. My maximum values here are around 2 e to the 8, which is significantly higher than the 1.3 e to the 8 computed in the textbook. Some of this is likely due to a stress concentration here on the edge. So if I move away from that stress concentration a little bit, you can see that I drop down into the 1.5, 1.6 e to the 8, which starts to compare very well with the answers in the textbook. So I hope this gives you a feel on how to use ANSYS Workbench to look at stresses in a pin due to a bolted joint, as well as look at the bearing stresses on the members of the bolted joint.